It's also the secret behind hex codes. Sorry, it literally just cut me off there. I have no clue what happened. Anyways, it's also the secret behind hex codes. So, hex codes, you might have seen them before. 0, 0, F, F, 0, 0. Congratulations. This is 0, 0 for the R, G, and B. So then this is 255. And this one's just 0. So that's green in hex code. It's a really neat trick. But it's, as I mentioned before, it's an online thing. It's gonna do that. So switching gears again, let's go and figure out how binary adding works. So 1, 0, 1, 0 plus 1, 0, 1, 0. We already did this before, but so if this is, then this is 0. This, it would be 2, but remember 2 is 1, 0. So 1, 0. Then this would be 1, and then this would be 0, and then carry the 1, so 1. So this is how you do that. Now, here's how you can represent it a cool way. So I'm going to do two completely different numbers. Let's do 0, 1, 0, 1 and 1, 1, 0, 0. This way we get every scenario. Here you can see we get 1, 0, 0, carry the 1, 0, 1. Now, you can see that this was a very bad example, but you can see we're adding 5 and 12 here, I believe. And then the answer we get should be 17. Yeah, you can tell, because I know that 4 bits is 15, and then so it would be 1 more than that, so 16, and then you add the 1 back, so 17. Anyways, so with that being said, you might be able to tell sort of what happens here. So if I get my pen out again, I can see that only if one of them, so like, see, I have an XOR gate here. Well, actually I should probably explain logic gates. Alright, looks like we're doing that this episode. This is an AND gate. And see, so if two things are here, represent 0. So this only outputs 1 when both of the inputs are 1. Otherwise it's just 0, which can be represented by this, the carrying factor, and it outputs a 1 right here. Congratulations. Next, we have the XOR gate. It's represented like this, with an extra stroke at the back. Don't forget that extra stroke. Exclusive OR gate. So now, it only outputs a 1 if either are on. If both are on, it's a 0, and if neither are on, it's a 0. So you can see that happening right here. One of them's on, bam. So we can already see pretty obviously that the output, my bad, is an XOR gate. Well, wait, hold on. You can see that the output is clearly an XOR gate. You can see when one of them is there, it's there. Technically with 3 inputs, only if one of them are on, or 3 of them are on. You know what? So, you have output is an XOR gate, as I already said multiple times, and this carryover right here is an AND gate. So if these two values are 1, then it makes 1. If these two values are 1, then it makes 1. Since these three values are there, then it makes a 1. Congratulations, you solved binary addition. Now, for subtraction, it's actually a pretty cool concept. If I have 1, 0, 1, actually, let's make it 0, 1, 0, 1, and then I want to subtract from it 0, 0, 1, 0, so I'm basically subtracting 2, so 5 minus 2. Now, normally you'd go about this in B3. Wow, you solved it using normal math, but we're trying to do it binary math. So here's how we would go about this. You have 5, and then what do you put down here? What do you put in this space? It's not 3. So basically, what we're going to do is we're going to take 3, invert it, and add 1. And then this is our new 3. If we add these and then ignore the last result, we should get 3. So basically, there's nothing going on here. We can just cross that out. We do not want that number. We get rid of the carry out. So now this would be 0, 1, 1. Oh, shoot, I did 3 by mistake. My bad. So I should be getting 2. And then this would be 0, 1, 0. So this is 2 because I accidentally did 3. So this is negative 3. And then this is 5. So the way that this works is I actually have no clue. But the way that it works mostly is by getting rid of this. Because if we add this back on, then it's no longer 2. It's actually 18. But because we put mod 16 on it, because it can't go to this number, we get 2. So this is not actually 2, it's 18, but we remove the last carry out. And this isn't actually minus 3. In fact, it is 13. Because 13 plus 3 equals 16. So, yeah. And 16 in this would be 1, 0. Yeah, it would be 1 followed by 4 zeros. So, congratulations. Now you know how to do binary subtraction as well. I already showed you the adding machine in my last video, and the subtraction machine is pretty easy for hex. Remember, this is the output. This thing needs to be on because, okay, why does this just look like a distorted face? But basically, x minus y. So now let's say we have here going y into the side, and we have here going x into the side. Then the output is x minus y. Now, I don't like working with hexadecimal because here's what it forces you to do. You either put this every other line, you can see this is already taking me a while to draw. Imagine what it'd be like to place it. Or you do something else really complicated, which is to, let me just move over here. You take 15 minus the input value. That should not be in parentheses. My bad. Whoopsies. 15 minus the input value, which is x. There we go, x. And so then you're going to subtract y from it. And then you are going to do 15 minus that again. So if you just remove these parentheses here, get 15 minus 15, which is just 0, minus x minus y. So yeah. Well, you would know that if you simplified this, it's not that, it's just x minus y. Alright. Sorry, not x minus y. I'm stupid. X plus y. Yeah, it gets annoying. So, yeah. So eventually, yeah, you get x plus y. And so, if I traveled y distance away, so this is x, 1, 2, 3, 4, 5. Then I'd have to do this whole circuit just so I could add back 5 and then get x again. You see that? Anyways, y is the distance you traveled. So that's what that is. That is why I don't like working with hexadecimal, because it's annoying. Binary? Sure, it's a simple question of is the redstone on or is it off? I can use repeaters. I can use literally any means I want. I can use just NOT gates are really easy. Now, I'm not saying that you shouldn't learn hexadecimal. It's a great one, like absolutely amazing. But I'm just saying, if you're starting out, learn binary, not hexadecimal. Hexadecimal is a pain. By the way, before we end, I just want to get something straight. ROM. Read only memory. ROM. It's pretty simple. With binary, did you know that you can lock repeaters? That's right. If you push a repeater into the side of another repeater, and then you power it, it turns like this, and it locks whatever states it's in, on or off. And so basically you have a bunch of those, or what you could do, otherwise, if you don't want to do that, is there's a new block that is basically perfect for this, and it's literally just a T flip-flop, but in one block. You heard what I'm talking about? It's the copper bulb. This thing right here. So, if for those of you who don't know what a T flip-flop is, I do not blame you. Here's what it is as a quick breakdown. If you power it, it turns on. If you stop powering it, it's still on. But then, if you repower it, then it turns off. Because that's how T flip-flops work. It's basically just toggling whether it's on or off every time you press it. So there you go. That's what a T flip-flop is. So now, where were we? Read-only memory, right? So if you were to take a bunch of these, and you were to attach a comparator to it... Wait, I'm not sure. Would a repeater work? No, it would not. I don't think it would. You guys can test that out. So you attach a comparator to it. So whenever you want to read this bit, then you do that. And that's simple. That's read-only memory. And to, set the memory in the first place, you just power it or you don't power it. Yeah, that's it. Another thing is just memory. It's the new, most efficient way to do this. So I have a copper bulb here. Now, let's say I want to read this. I don't know why it keeps doing that. I have a command block here that's like beep, boop, boop. Set this to a command block with values that will take this value, whether it's on or off, and put it to this area. Now this area sets it to where it needs to be, and also destroys the command block. So that's how that works. And whenever you want to write to it, you get another command block. And then this command block's just like, you know what? Put this redstone block on top of this. And that's how you toggle it. So basically, you can be like, if you want it to be off, then you can set this to be here. You can set this little guy here. And then, if it gets a value here, then this command block's job would be to place a redstone block here to power this, to turn it off. And then, again, you'd have something like maybe a repeater tick display that would just like, it's hooked up to another command block that just removes that redstone block. And yeah, that's basically how this works. Where even is the start of this? Wow, there is quite a lot here. Quite a lot. Like, actually, this is insane. But anyway, yeah, that's it for today. I hope you learned